Okay, so we can go on with measuring instruments. We have about, 14, 15 minutes left. Right, so under measuring instruments, so basically what we're going to look at is, this used to be chapter 13 in the textbook before the updated syllabus. So we're going to take a look at range extension. So range extension is basically how we're going to implement our measuring instruments as voltmeters or current meters. So we'll take a look at why we do that, because there is a specific reason. We'll get into it in a moment. Then we can also take a look at how we can implement a wattmeter and how we do measurement of resistance as well. There's actually two methods of resistance measurement that we'll take a look at. Okay. So the reason why we do range extension is or the main reason for it is because it's very impractical to build measuring instruments to operate at high voltage or high current. So we make use of things like resistors and instrument transformers to help us put these measuring instruments in high voltage and high current circuits. Now, in AC circuits, we make use of instrument transformers, so like we have here. So there's a potential transformer for a voltmeter. So what that does, it steps the voltage down to a safe level for the voltmeter. And then we have a current transformer that's basically just a few turns around the conductor that we have current flowing through. And that basically acts as a step-up transformer to feed an ammeter. So basically, it brings down the voltage for the ammeter, steps up the voltage, will bring down the current, and and then we can also, using this method, so a current transformer and a potential transformer, to make a wattmeter there with a current coil and its voltage coil there. And then in DC circuits, we make use of shunt resistors to make ammeters and multipliers to make voltmeters. Right, so the first one that we have here is the shunt resistor. Now we typically use them to form ammeters from our measuring instruments, and so they're basically used, or rather the size that we pick for these resistors are such that you will have what we call full scale deflection. So basically your maximum reading on the meter when the when the current is a maximum. Goodness, I actually completely butchered that. But yeah, so if we take a look here, the meter is then connected in parallel with the shunt resistor. So the shunt resistor will take basically the bulk of the current through it and will only allow a small current then to go to the meter that can be measured. So this is basically a scaled down, how can I put this? Yeah, so you basically have a scaled down current going to your meter instead of the full load current, and potentially creating a small fire with your meter there. So in order to calculate this value for the shunt resistance, we need to know what the resistance of our meter is. We also need to know what the maximum current through the meter can be at full scale deflection. So meaning when we measure our full load voltage or our maximum load voltage, full load voltage, maximum load current, my goodness. And the maximum load current is also what we're going to need here. So basically what we end up with, the voltage across the shunt resistor is same as the voltage across the meter, which means that the shunt current multiplied by the shunt resistance is equal to the meter current multiplied by the meter resistance. And that means the shunt resistance is then the meter current times the meter resistance divided by the shunt current. And the shunt current is just then your full load current and or maximum load current minus your meter current. And then we also have the multiplier. Our multipliers are used to make voltmeters out of measuring instruments. So in this case, we make use of series resistors to basically extend the range of our voltmeter. So basically, you're going to have the bulk of the voltage sitting across the resistor here, and yeah, so basically this resistor is going to limit the current through the meter when the supply voltage is going to cause full-scale deflection through the meter. Right, or rather, yeah, so basically when the supply voltage measured is a maximum. Right, so our meter current at full-scale deflection is what we're going to need to calculate the multiplier resistance. And we also need to know what the maximum value of the supply voltage is going to be. Then basically the supply voltage is equal to the two voltages across the multiplier resistor and meter resistor. And so these voltages are also, so you're going to have the same current flowing through both of these resistances. So then eventually you end up with multiplier resistance calculation that will look something like this. So you're basically calculating the total resistance of the branch minus the meter resistance. So you guys will see sorry guys, you guys will see that with the shunt resistor, it's going to be usually quite a small resistance that you're going to have here because it needs to take a lot of current away from the meter. And here, the multiplier is typically going to be a very big resistor to take up the bulk of the voltage on it. Right. Okay. Now, yeah, so let me just get to the example here. So we can also make a wattmeter. So wattmeter is actually just an ammeter and a voltmeter combined. So this is how you would place a shunt resistor and a multiplier resistor with a wattmeter. So yeah, so this part here is technically your ammeter, and this part here is technically your voltmeter. Okay, so we have a bit of an example here. So we have a moving coil meter with a resistance of 8 ohms, and full-scale deflection occurs when 12 milliamp flows through it, and the instrument is to be modified to give full-scale deflection at a supply voltage of 250 volts. Draw the circuit diagram of the modification required, including the value of the additional component. Right, so the modification is the addition of a multiplier resistor. So that's basically, here's our circuit diagram. So this is usually how these questions are asked. And yeah, if we take a look at our series resistance here, how we calculate it. So you just take your formula, stick all the values in, and you guys see we get then 20.825 kilo ohms here for our for our multiplier resistor here. Right. So pretty straightforward. I'll do a few exercises with you guys tomorrow. I don't think we're gonna have enough time to do one now. So I think, yeah, think we can go on with this tomorrow, and yeah, if we don't finish up tomorrow, maybe on Friday we'll be able to finish up. Right, guys. Yeah, so if you guys don't have any further questions, have a good afternoon, and I'll see you guys tomorrow. Cheers.